In this session, we are going to cover a type 1, type 2 error of a test concerning the mean of a normal population. We are using Wolfram Alpha's demonstration website to demo this. So let's start with the hypothesis. The null hypothesis is mu equals mu naught. Alternative hypothesis, mu greater than or equal to mu naught. And we are going to assume initially that the alternative hypothesis, the mean mu equals 1. And we are going to assume that the null hypothesis mu naught equal to 0. And the population variance for both populations is 9. And a sample size is 10. And the boundary or the critical point or the cutoff point is 1.5 for us to make the decision. So now let's focus on the right hand side here. For testing our hypothesis, we compute the test statistic, and if the computed test statistic is greater than the critical value, then we reject the null hypothesis. So now let's come back to the graph here, the top graph here. So this is the distribution of the test statistic. So in this case, the test statistic is the sample mean x bar. And this chart represents the sampling distribution of x bar when the null hypothesis is true. That means the mu naught equals 0. So using central limit theorem, we know that the sampling distribution of x bar is distributed normally with mean 0, mu naught 0. And the standard deviation is sigma over square root of n. In this case, sigma is 3. And divided by square root of 10, so it's a little less than 1. So on the x-axis, x bar is plotted, and you can see that the possible values of x bar is anywhere between -3 to +3. And in terms of making the decision, the critical point, we are using 1.5 as the cutoff point. And if x bar is less than 1.5, then we know that x bar is very close to mu naught, and then we decide that we quote unquote accept the null hypothesis. But if x bar is more than 1.5, then we say that we reject the null hypothesis. So the right tail area here, and that is it's called significance level. You see up at the top here it's 0.05, and that's also called alpha. So the way we are structuring this decision is that even though x bar comes from this whole distribution, when there is only 5% chance that x bar is greater than 1.5, so if our computed x bar is greater than 1.5, we are going to reject the null hypothesis. So the way we are setting up this decision is that the alpha, that is probability that I will reject the null hypothesis when it's true, that's also called the type 1 error. So the probability of type 1 error that equal to alpha, that is equal to 0.05 in this case. Okay, and then 1 minus alpha, that's on the left hand side here. So that means that the probability that x bar is less than 1.5, that is 1 minus alpha, in this case 95%. That's called confidence, and that is the probability of making correct decision. Because x bar is less than 1.5, then I'm going to say that I'm a quote unquote accept the null hypothesis, so I'm making the correct decision. Okay, now let's focus on the bottom chart here. So this is when the alternative hypothesis is true. So alternative hypothesis, we said the mean is 1. So the again, I'm plotting the x bar, the sampling distribution of x bar from this population of mean 1. So you see the peak is at 1. And the same cutoff point, 1.5, I'm using. So you can see that whenever x bar greater than 1.5, I'm going to reject the null hypothesis. In this case, what it's called power here, it's like a 30%. So this tail area on the right hand side is 30%. So there is a 30% chance that x bar is greater than 1.5 because the mean is 1 here. So you can see that the distribution is shifted to the right here. And so the probability of making the correct decision is this 30% because the null alternative hypothesis is true. I am rejecting the null hypothesis. That is true. So that's a correct decision that is depicted by the right hand side here. The left hand side is the mean is less than 1.5, the sample mean. So I am accepting the null hypothesis, quote unquote, but actually the alternative hypothesis is true. So the wrong decision, the probability of that is 70%. So the beta equal to, in this case, the probability of quote unquote accepting the null hypothesis when null hypothesis falls, and that is called the type 2 error. So probability of type 2 error is 70% in this case, and the right hand side, this area is 1 minus beta, which is the power, and that is the probability of correct decision, making correct decision. Alternative hypothesis true, I'm rejecting the null hypothesis, that's a correct decision. And you can see that the error is, the beta error is pretty large here, because you see there's a huge overlap between the null and alternative hypothesis. When there is a big overlap, then the X bar come from either one of those. So intuitively you can see that that's one of the that's the reason why this error is pretty big. So now what I'm going to do is the alternative hypothesis, I'm going to change that to the mean equals 2. Now the distribution is shifted to the right. You see the peak is a 2. So now the power is 70%. That is 1 minus beta. Beta is 30%. So you see that the type 2 error is getting reduced when I'm moving the distribution to the right. So now let me change the mean of the alternative distribution to 3. Now you see that the alternative distribution is shifted even further to the right. So there is the two distributions are farther apart now. Then when you look at the power, it's 94%, but the beta is 6%. So you up at the top, alpha is 5%, beta is 6% in this situation. So intuitively, when the two distributions are apart, then you see that alpha, beta are small. That's what we want. Now let's see that how we can improve this the alpha and beta errors. So let's focus on the variance here. So let's say that the variance, population variance instead of 9. So let's say the population variance is close to 5. So in this case, you see that the two distributions have become skinnier and taller. And you look at the alpha value, alpha is 0.02 and beta also 0.02. So what we are doing is when the variance is getting reduced, then the two distributions are farther apart, then you see that the two errors are getting lower. So now let me go back to the what we had before. So we had the population variance of 9. So let's go to that, 9.0. And then let me increase the sample size from 10. If I increase the sample size to 40, okay. So again, you see that the two distributions skinnier and taller. You see the significance level or the alpha is 0.0007 up at the top and the bottom, beta is 0.001. So again, by increasing the sample size, the both errors, alpha and beta, are getting reduced. So let me go back to the situation we had before where the sample size was 10. Let me type it in here, sample size 10, the same situation. Remember, alpha is 0.05, beta is 0.06. So now what I'm going to do is change the critical value. So arbitrarily, I can change the critical value. Instead of 1.5, I'm going to change the boundary to, let's say I'm changing it to, say, 0.8. So now you see that alpha has gone up to 0.18, but beta has gone down to 0.02. So both alpha and beta are related. So when alpha is going up, you see that the beta is going down. And let me change the boundary value or the critical value to something else, 1.96. Now you see that alpha has gone down to 0.02, the beta has gone up to 0.14. So there is a trade-off between alpha and beta. We cannot minimize alpha and beta simultaneously. When we increase alpha, then beta is going to get reduced and vice versa. Okay, so in real life, how do we balance alpha and beta? That determination is based upon the consequences of type 1 and type 2 error. Understanding the consequences of type 1, type 2 error would help us choose alpha and beta appropriately. So let's talk about a quick example. So let's go back to the emission example. So let's say that EPA is requiring the car manufacturers to be carbon emission compliant. Let's say that the required law is the mean carbon emission mu is less than or equal to 5 grams. So the null hypothesis is mu less than or equal to 5 grams. Alternative hypothesis mu is greater than 5 grams. So when we do the testing, let's say they tested 10 cars and the alpha is 5%. So 5% of the time the null hypothesis is true. That means the car is compliant, but we are going to reject the null hypothesis. We are going to make the decision that it's not compliant. So what is the consequence? The car manufacturer has to pay a penalty, pay a fine, millions of dollars to EPA. So the car manufacturer would want the alpha error to be much lower than 5%. On the other hand, if we look at the alternative hypothesis and look at the type 2 error, so let's say the alternative hypothesis is true, so that means that the car is not compliant, but then by this sample, we are accepting the null hypothesis that it's compliant. So we are committing type 2 error. So then what is the consequence of type 2 error? The society is going to live with higher emissions. So EPA is representing the society. So now the EPA and the society would want this type 2 error, the beta error, to be very, very small. So now if we make the beta error small, then alpha error is going to go up. So the car manufacturer and EPA, they have to negotiate between the two of them and then do some of these scenarios what I did here. So they may increase the sample size from 10 to 40. So in which case both the type 1, type 2 error are going to go down. Still there's going to be a trade-off, but overall it's going to go down. So, but it's not going to be cheap, it's going to cost money. So the car manufacturer should be willing to invest money on doing more tests. So then the alpha and beta error can be appropriately determined. So the bottom line is we need to understand the consequences of type 1, type 2 error before determining the alpha and beta value for a test. Thank you.